All right. In this example 4 from 119, we're looking at the map of t from R3 to R3, given by the transformation shown here, and 2x minus y, x plus y plus z, and 2y minus z. We're trying to find three things for this example. We want to find t inverse. If it exists, we want to find the image of t, and we want to write down a basis for the transformation. Okay. So those are kind of like the three pieces. So first, let's find the matrix that corresponds to this transformation. So call that matrix A. Looks like it's going to be 2, -1, and 0. 2 is going to look like a little 0 there. This is going to be 1, 1, 1, and then 0, 2, and -1. Okay. Um, all right. So we're going to go ahead and construct our matrix again in Maxima. We have the matrix to -1, 0, 1, 1, 1, and 0, 2, 1, -1. Okay, and so in this case, we're looking for the inverse, so we can determine the determinant of A. If that's not equal to 0, then the inverse exists, and we can calculate the inverse by writing inverse of A. I think it might be invert. There it is. Okay. So the command for computing the inverse, the determinant is -7, which is non-zero, and the inverse of A is given by this. So you can factor out actually the 1/7 from each of these and write that in the front if you'd like. And that will be the inverse of A. And I think the other two we'll just jump back over for from technology back to the paper to finish off this example, since both of those are pretty straightforward with respect to what is being asked of us to solve. And so here we are back on the paper. And so the inverse we already saw, and we just had that there a second ago. So GeoGebra told us that T inverse, or A inverse, if you will, the inverse matrix for this transformation is 3, 1, 1, -1, 2, 2, and -2, 4, -3. And we're going to multiply all that by 1/7. So factoring out the common element of 1/7. This is the inverse of t. Okay. So that's part A. Part B was the image of t. And so the image of t is the result from the span of each of the vectors. In other words, if you think of these as columns, then we can write this as x, the variable x, as 2, 1, and 0, plus y times -1, 1, and 2, plus z times 0, 1, and -1. So this, then the columns of this describes the image um, of E. In other words, since the determinant of A is non-zero and it obviously an inverse exists, for any vector x in R3, p of x is a linear combination of the set 2, 1, 0, -1, 1, 2, 0, 1, negative 1. Okay. So it's a span of this would be in the image of T. Okay. And that actually answers then part B. So this would be our basis set here. These are linearly independent, and they span all of R3. So this is here, see it. This is then the basis set from which since these are each linearly independent and they span all of R3, then that's a basis set for our transformation, and any vector x that is transformed by this vector, by this matrix, or by this transformation will be in the span of this set. Okay. All right. So I hope that was helpful, and I'll see you in the next example.